السلام عليكم ورحمة الله وبركاته. بسم الله والصلاة والسلام على رسول الله. My name is Muhammad Mustafa Wahaiba. My tech number G is 53608. My presentation today about evaluation of 5G and FSS coexistent in indoor scenario of Malaysia. My supervisor, Prof. Atawadi Saleh, and my examiner, Prof. Aliani Ismail, and my coordinator is Prof. Sharifa Mumtaz. So first, we have the outline, introduction, problem statement, objectives of the project, research scope, lecture review, methodology, result and discussion, the optimum resolution zone between the 5G and FSS, conclusion. Introduction. Etisalat offers 5G broadband speed with the 5G wireless access point. 5G wireless router coming soon. All indoor should be connected to 5G wireless network shortly. Mobile data traffic has grown substantially in recent years in order to meet traffic demand over the next decade, and existing network capacity multiplied by 1,000 will be required. Therefore, the primary means of freezing network capacity by small, low-energy cells of 5G network size. Mobile communication industry experience huge transformation with the every passing day. A new generation and standard are being established to providing register, subscribe with the voice data and multimedia service at increased speed. As we discussed with the MCMC, the Rigscape about the new generation for the frequency 5G. And this picture show the discussion. Decision was taken at the 2015 World Radio Communication Conference to discuss on 3.3 GHz to 4.2 GHz, as known this range for the C-band to future mobile broadband. 5G beamforming and 5G multi-antenna structure. This encouraged service providers to use this band for future 5G system to ensure easy deployment. For this project was focused in indoor frequency 3.5 GHz band, especially from 3.4 to 3.6, as we shown here in the figure coded by the MCMC. So before the FSS was using the whole C-band from 3.4 to 4.2. Now the FSS was sharing the 5G, the same band, C-band. 5G will use from 3.4 GHz to 3.6 GHz, and the FSS will use from 3.7 until 4.2 GHz. We have the problem statement here. There is a possibility of frequency interference with the planned allocation of 5G network and FSS system due to the technology complexity of FSS service with the 3.5 GHz range. Reflected with this by permitting unnecessary signal from 5G base station and mobile terminal to interference with the FSS earth station receiving signal. Here the received signal uses the same frequency of the 5G. So in the 3.4 GHz as shown in the figure. So the problem will be interference from the signal that download from the satellite to base station, especially if the base station of the 5G is near from the base station, the earth base station for the satellite, because the signal will be coming from long distance, from like 1,000 kilometers, and the 5G will be a strong signal and will affect on the 5G and the FSS base station. So the objective of this project, we have two objectives. The first one, to connect measurement operation for 5G and FSS existent in indoor environment in Rigscape, Cyberjaya, Selangor, Malaysia, to analyze and evaluate receiving signal due to the 5G and FSS coexistent in indoor environment in Rigscape. So we have the research scope. Our focus here in the C-band application. So C-band application will use by two application or two system, 5G system and FSS system. So the coexistent study between 5G and FSS will have like optical excitation zone should be like divided the frequency. So divided frequency spectrum range for 5G would start from 3.4 to 3.6, and for spectrum analyzer for the spectrum range for FSS, which should start from 3.7 until 4.2 gigahertz. Here we have the lecture review and the important point for the lecture review when mentioned by the topic and the author and the years and the year. So the first point, the low frequency network using existing cellular and Wi-Fi channel benefit from more useful encoding and wired channel size 100 megahertz to research speed 25 gigabits per second to 50% faster than LTE. That means the Wi-Fi of the 5G will be faster than the LTE. So this written by Batzold in 2015 under the top book article. It's 5G radiance on the horizon mobile radio. The other point, the 5G is providing three main types of service. We have enhanced mobile broadband, ultra reliable low latency communication, and massive machine type communication. The other point, it's talking either about the 5G, the small cell are planned, the 5G small cell are planned in combined with the indoor and outdoor. The speed indoor 10 gigabit per second and low radiance of cells about 150 meters. So here we will talk about the FSS and the C-band. This one written by Hyoji in 2008, and the information said the FSS application in the range of 3.4 gigahertz to 4.2 gigahertz included large satellite earth stations that act as a portal from satellite space for trunk or network traffic. Sharing FSS, this one under topic article called Sharing FSS Satellite C-band with secondary small cells and deed communication. The last point is talking about the Malaysia frequency, how they divide it. Like for the indoors, take it like 3.3 to 3.4 gigahertz band for limited indoor, and the outdoor 3.4 to 3.7, and for the satellite FSS used from 3.8 to 4.2 gigahertz. It was not that between 5G and satellite used the ground band, or as known like forbidden band, would be used in different range, like 20 mega or maybe 50, or if it's possible, we'll use like 100 megahertz. This one published by Tan and Leon and Zhu like in 2018, and the topic was consistent analyzing between 5G system and fixed satellite service and 3.400 to 3.600 megahertz. Then we will move to the methodology of our project. We have the lecture review. As we said, it's talking about many points about the C-band and FSS and 5G and the IMT advanced parameter and the specification BSAT and interference type and scenario. Then we move to the methodology. The methodology, we have the experiment like the location of the base station and antenna receiver in indoor. So then the measurement will take like a setup for RF level between the TX and RX antenna. Then we have the varied location separation distance, different FSS bandwidth, and we have the model we use like line of sight and non-line of sight, and we have the collection data by using the spectrum analyzer and PC and MATLAB, and we have the result. So the measurement here, we have the 5G base station, 3.5 gigahertz, the frequency is 3.5 gigahertz, and the power transmitter is about 10 to 35 dBm. And then the receiving band, we have antenna receiving, it's the range for 650 megahertz until 8 gigahertz. The spectrum analyzer is about 100 gigahertz to 6 gigahertz. And here we have the PC collection and analyzed using the MATLAB. So we have the scenario of the measurement. We have three scenarios. We have inside the Rickscape, and we have CyberView. This is between the CyberView and Rickscape. It's about 131 meters, and we have scenario from Rickscape to MISAT with a distance almost 3 kilometers. MISAT is one of the most important companies in the FSS signal. Then we move to the propagation length model. So as we mentioned before, we have indoor and indoor base station inside the Rickscape with the high almost 2 meters, and we have the receiver signal with the high almost like 80 centimeters, and the distance between TX and ARCs about 1 meter to 3 kilometers. First result propagation length model. So we have the first one here. As we shown here, the map is for the Rickscape. Inside the Rickscape, we have the 5G base station here inside the hall. We have one point, it's line of sight, and the yellow color show us the power, the coverage of the power transmitter signal for the 5G base station about 35 dBm, and the distance about 1 meter to 55 meters. All these points range from 1 meter to 55 meters. We have here the first point. The first figure, this blue figure, show the screenshot of the spectrum analyzer, and both use the MATLAB, like two figures by MATLAB. So we have here in the distance between the TX and ARCs about 5 meters, and the highest received power signal, it's like the maximum, it's about minus 3.53 dBm, as shown here from the figure. MATLAB also here in the spectrum analyzer. And the frequency about 3.46, and the frequency starts from 3.3 to 4, and with the center frequency 3.5. The span's about 1 gigahertz. Then we have the other point, it's about 15 meters, and the power receiver signal minus 13.41 dBm, and the frequency signals about 3.48 gigahertz. The third point is about 20 meters, and the receiving power signals around minus 28.41 dBm with the frequency 3.48, and the average power frequency level is about minus 52.37 dBm. And we have like and the distance with 45 meters, the receiver power signal is minus 53.60 dBm, and the frequency in this signal is about 3.43 gigahertz. As shown here, this is like minus 53.6 dBm. And the last point was taken is in distance 55 meters, receiver power signal minus 57.88 dBm. The frequency signal is 3.46, as shown here in the spectrum analyzer. Then we move to another scenario. That scenario, as shown in the green color, the coverage of the powered 5G base station signal about 10 dBm, and the distance from 1 to 45 meters. And the red color, it's like we don't have signal here, we can't reach the signal here. So we have the first point in 5 meters. The highest receiver signal was minus 23.35 dBm at the frequency 3.49 gigahertz, and the range of frequency starts from 3 to 4, and the frequency center is the same, 3.5 gigahertz. We have like the other signal, it's about 20 meters. The received power signal is about minus 44.6 dBm. The frequency signal is 3.42 gigahertz. As shown here, like minus 44.60 dBm. the highest peak we can reach. And the distance between TX and ARCS was 35 meter, and the power transmission was 10 dBm, and the receiving power signal by using the Yagi antenna was minus 54.61 dBm, and the frequency signal is 3.423 gigahertz. And here, in this scenario, we just comparing between the result outside the building. It's near from the building. It's outside. This is the 5G base station, and this out around the building. And this one, we just make sure there is like obstacle wall, like cement wall or glass wall, and we want to compare the result between them. So we have the first one. It was like distance between TX and ARCS, 35 meter obstacle glass wall. So the received power signal was like minus 52.35 dBm. This is the maximum power receiving signal. And like the average of the received power signal, it's minus 72.59 dBm. With the frequency 3.45 gigahertz. So the signal is good here. And if we compare it with the obstacle cement wall, the signal will be like less than at the same distance, but it's like decreased to minus 71.01 dBm. And then the last scenario was taken in the 15th of November 2019. It was just to measure if there's signal in MESAT, here in the MESAT or in the CyberView. So the CyberView, the distance 131 meters, there is no signal, and the power received signal almost minus 72.53 dBm. And the MESAT about like 3 kilometers, and the received power signal is minus 19.58 dBm. In this figure, in this slide, the distance model between TX and ARCS antenna comparing the distance and the receiver power signal. So the distance with the 10 meter distance, the power receiver signal was minus 13, and with the 20 it was minus 30 dBm, and in the 13 it was minus 41 dBm. So when the distance increased, the power level decreased. So the power receiving is minus 57 at 35 meters, as shown here in the figure, +1. So we have on the 14 meters, the power receiver is minus 52.53 dBm, and in 15 meter we have minus 61.19 dBm, and in the 131 meter, this one in CyberView, there is no signal. Also in the MESAT, also there is no signal. Here we just compare them between path loss with the kilometer and meter. As in kilometers, the range of the path loss starts from 40 until 80, and our Fox interesting like a frequency from 3.4 gigahertz with the line dash green line dash. This one at like almost 18. The maximum start like from 40, going with linear relationship to 18, and here in the meter. We have the range from minus 28 to 20. It's less than kilometers, and our 3.4 gigahertz is about like increase with the distance, linear increase with distance like until 28 with the distance 100 meters. Here we compare them between the result in the same day. So here on 25/9/2019, we have like almost 11 points, started from 5 meters until 60 meters. The highest point we can get in 5 meters minus 35.53 dBm, and the lowest was in minus 72.19 dBm, and distance 60 meters with the frequency 3.47. So we have comparing between power receiver signal and distance meters and frequency with gigahertz. Also here, when we meeting with the MCMC group, we just take like almost 5 points. We have like the average of receiving power signal at 1 meter is minus 54, 0.34, and the lowest receiver signal was in -73.49 dBm. Here there was the third day. We went there on 8th of October 2019. We just focus on the outdoor or just out the building. Like we make circle and we take the result from like 30 to 45. So the lowest, the highest frequency was, the highest receivable signal was -17, and the lowest receivable signal was -72.78 at distance of 45. And almost the frequency, it's the same, yeah, the frequency. Then we move to optimum excitation zone between the 5G indoor model and FSS. So from the table here, the power transmission for the 5G station, it's about 10 to 35 dBm. And the location of 5G station, the location of the base station is inside the Rickscape building. And the frequency band from 3.4 to 3.6 gigahertz. And the maximum distance for the signal receiver is 60 meters. And the Rickscape, so the Rickscape closing set using the FSS MESAT, it's about 3 kilometers. It's like far distance and it's safe. And the MESAT frequency started from 3.700 megahertz. Also, like there's like 100 mega forbidden band. This one, it's like less interference will happen if there's like interference, but we don't have like any interference here. So the conclusion, this work achieved all the state objectives. The check result obtained from the study and observation described and analyzed in this research. Originally, the performance evaluation of the 5G transmission with the power equal to 35 dBm result in higher data receiving than widespread power recording. The second one, the power output of the 5G indoor base station declined to 10 dBm due to the reduction in the scatter size. The range of power receiving started from -3.53 to -57.88 dBm when the power transmitter is high. The nearest center using FSS transmitter and receiving signal in MESAT, the lowest frequency used by MESAT is 3.7 gigahertz, and the distance are around 2.99 kilometers from the indoor antenna Rickscape. In the end, there is no interference between the 5G indoor signal and the FSS signal in this scenario measurement. At the end, I want to thank you for your time and for your listening, and I appreciate it. Thank you so much.